Yeah, I hope the screen is visible, right?
Yes, it is. So Arnab,
Okay.
let me just quickly introduce you and
Yeah.
then.
Yeah, sure.
So today we have with Arnab Maiti with us, who is a third-year PhD student at University of Washington. He was also a visiting researcher at Leeds MIT, and before this, he was an undergrad at IIT Kharagpur. His work focuses on mostly algorithms for problems at the intersection of game theory and learning theory. I am always excited to hear about his work, and today he will be talking about his recent Colt 2025 paper in the area of online learning on graphs under Bandit feedback. So, without much ado, let's welcome Arnav, and over to you.
Yeah, thanks a lot for the introduction. Yeah, so this is one of my works in on the online learning area that I kind of recently started exploring, and this was the part of this work was done when I visited MIT last year for my summer internship. So G1 is my MIT co-author. He's also a student at MIT, and then this was Gabriel is the professor who hosted me there, and Kevin and Lillian are my advisors. So I'll get started. So in this like talk, like I'll be focusing on this very classical problem in the learning theory, which is called online shortest path in directed acyclic graphs. So in this problem, like you're given an input graph which is directed acyclic, and we assume that there is like a single source and a single sink. And typically in this setting, what happens that in each round T, an adversary comes and chooses the weights of these edges. So all some loss values for these edges. So I'm going to denote it by YTE, which denotes the loss of the edge E in round T. And as a learner, my goal is to choose a path from source to sink, and I incur the total cost of the path as my loss, which is the sum. In this case, if I choose this particular path, then I incur like YTE1 plus YTE2 plus YTE3, and we are in the bandit feedback setting, so I observe only the total loss as my feedback. So I don't get to see what these individual values were or what the values of the other non-chosen edges were. I only get the feedback of the total cost that I incurred. So some mathematical stuff like pretty straightforward. I'm just like introducing. So like by GV comma E, I'm just denoting the directed acyclic graph where V is the set of vertices and E is the set of directed edges. And for any node V, this delta minus V denotes the set of all incoming edges to the node V, and the delta plus V denotes the set of all outgoing edges from the node V. So some standard notations. Now, mathematically, I'm going to denote the set of paths from source to sink as a combinatorial set, and each path is essentially a combinatorial vector, 0, 1 vector, and it is indexed by the vertices and the edges. So essentially, uh, I say that like the xv is equal to 1, like the index v is 1 if the vertex v is part of the path, and similarly xe is equal to 1 if the edge e is in the path. Otherwise it's 0. So it's like it's 1 and 0 just denotes whether the particular element is included in the path or not. So just the standard notations in that sense. And this is a very well-known combinatorial object, which is like the convex hull of all paths from source to sink that just forms the flow polytope. So in the like this polytope is just defined as follows: like from the source, flow of one kind of comes out, and in the sink, like the flow of one kind of goes in, and in the intermediate nodes, the amount of flow going in is equal to the amount of flow going out, and that's what is kind of captured by this equation here, and that's gonna be the convex hull of all the paths from source to sink. And this is like a very efficient, like this is like a very good object because you can do optimization over it very efficiently. So that will be the kind of the motivation of this talk. Like, can you come up with efficient learners for this particular problem? So mathematically, what we'll be doing is, like, in each round, we'll choose some vector xt from the set calx, which denotes the set of all paths. And an adversary simultaneously, like, chooses a loss vector yt. Now, like, just to be clear, like, it only assigns loss to the edges. So this is just an extended representation. So the values corresponding to the vertices will be given a value of 0. So the vertex themselves don't have a loss, just for clarity. And then the as usual, like, when a learner chooses xt and the adversary chooses yt, I incur like a loss lt, and I observe only that particular loss as my bandit feedback. And the goal here is to minimize regret with high probability. So like, regret is just the difference between the sum of losses that you incur minus the loss of the best path in hindsight. And I want to give a high probability regret guarantee here. And just like final few.
So no, you are choosing flows and not like really integral path URL, like
No,
calligraphic.
I'm choosing integral path. So
Okay,
I'm choosing
okay,
ht from calx.
okay, but
Yeah.
like, okay.
Yeah, so the idea would be pretty clear. Like, once you have a flow, then you can sample a path out of it.
Right, yes, fine.
Yeah, so that
The
would
flow
be the idea.
decomposition.
Compute the flow and then, like, sample a path.
Okay.
But that would be crucial for the estimators I construct moving forward. Yeah, so so this is the regret, and I'll be choosing like paths in each round. And some final few notations, like ft is nothing but the filtration that gets generated over rounds, and this p subscript t and e subscript t is just the expectation conditioned on the past filtration. And we allow the adversary to be adaptive, that is, like, based on the past filtration and the agent's algorithm, it can adaptively choose the next loss vector. So this is the final few things. And yeah, this is like the standard assumption that they have in the bandit literature for linear bandits, is that the loss of paths is bounded between -1 and 1. So if you take any path, the inner product will be between -1 and 1. It's like kind of normalizing it between -1 and 1. Yeah. So, okay. So now I'll get started. Oops, sorry. So typically, like, in linear bandit literature, like, the algorithm on your screen is kind of the most common standard algorithm that's being deployed. Like, you essentially, like, do some form of exponential weights over each and every path from source to sink, and that you also mix it with some kind of distribution, like based on the Kiefer-Wolfowitz kind of stuff, and you compute some distribution, and you define some loss estimators based on covariance matrices and its inverse, and you do the exponential weights. And here it's a biased version to ensure that you get high probability guarantees. And this algorithm is pretty good. Like, you'll get a regret guarantee which scales as square root dt log cardinality, which is like minimax optimal. And for DAGs, in this case, like, d is like e, like the number of edges. So, like, this algorithm is like nearly minimax optimal. So in terms of regret guarantees, we are fine. But the issue is that there's no known efficient implementation of this algorithm, because, again, like, you are like doing exponential weights over every part, and there are some additional components here, like computing this bias and all, uh, which makes, at least for now, it is like an open question, like, how do you come up with an efficient implementation? Like, if you were only concerned about guarantees in expectation, then there were some papers where they come up with some nice spanners and all. Like, essentially, spanner essentially tries to find some small distribution, and you mix it with the exponential distribution. But in general, like, at least for this high probability guarantee case, no there's no efficient implementation of this algorithm. So
So
the
Arnab,
question,
just to clarify, in
yeah,
the algorithm that you showed before, so the bottleneck is the exponential weights and not the Kuiper-Wolf weights, because I believe that Kuiper-Wolf weights can be solved like in polynomial time,
which
even for
one?
exponentially large sets. So
Which one?
when you say that do this Kuiper-Wolf weights exploration, like
Yeah,
GT and all, so I think
yeah,
that can be estimated, like you can have a like
yeah, yeah.
approximate
GT,
Kuiper-Wolf weights in
yeah,
polynomial time.
the GT can be estimated, but
Hmm.
now the thing is that it is not known to me at least whether you can uh, then like go and implement this exponential weighted algorithm in an efficient manner.
Right.
Because okay, like say if you just had if you didn't have this bias terms, right, which is essentially doing this, then recently there have been some papers where they show how to efficiently implement uh, this exponential weights over some combinatorial sets, but that requires this part to be kind of a linear kind of thing, like it has to be some linear function, but here you have like a
Mm-hmm.
quadratic term, so that kind of stops you from doing anything efficiently, at least as far as I know.
Makes
um,
sense.
yeah, so that's why I am not I'm not ruling out any algorithm, but nobody has like shown it probably that you can come up with a efficient version of this thing.
Mm-hmm. Got it.
Plus,
Yeah,
it, like the PT, the distribution is over paths. So
yeah,
this
distribution is
matrix, like
over
the
path.
KW matrix, would be huge. Like
Yeah,
No,
yeah, yeah,
but the
yeah, yeah.
KW matrix can still be solved. It's like a polynomial in the dimension. So it
yeah,
will
yeah.
only
But the
have
point
support over
is,
the dimension many set items.
yeah, but implicitly it's a huge matrix, right? So I don't know how you'll invert it. Like so, like GT inverse, like
So GT is a D cross D matrix, right? It's not
or is
huge.
yeah, okay. So
Yeah,
maybe
yeah.
yeah, yeah, is it a like what's the dimension of the
So GT is like, as Nija was telling, like GT is like a D cross D matrix. That's not going to be an issue, and I believe like you can definitely compute this like using them up in an approximate manner. The
yeah.
the issue, in my opinion, not comes in this part, but more like in like actually like sampling efficiently from this distribution,
Yeah, yeah, yeah.
Yeah.
because of this bias term which is like quadratic in nature. So I right now, like if there was no bias term, then you were kind of okay, like there were some algorithms which are already does that, but the bias term is introduced because they want high probability guarantees, not just in expectation. So
Okay.
if you are happy with just expectation, yeah, then there's this paper by Ella Dozen on volumetric spanners which does this exponential weighted thing in an
Yeah.
efficient manner. Yeah,
Makes sense.
but they're able to do it because they're kind of leveraging the fact that in the exponent it's like there's a linear term
Yeah.
here. But the moment you add this term which is not linear, like this, like no
Mm.
at least quadratic, so
Mhm.
then I don't know of any method that achieves a good like efficient implementation. Yeah, so that's why that was kind of the motivation, and also like the flavor of the algorithm itself. But yeah, so that's why like we are kind of motivated to ask like
So
what is
this
like
would be like a similar issue even in like follow the perturbed leader kind of settings.
yeah, like in follow the perturb leader, the main issue would be like how do you sample from the distribution that you
Right,
propose.
right.
Yeah.
Yeah, yeah, yeah. Yeah.
Yeah,
It's
so that's the thing.
it's
Like
okay.
if this thing was a continuous distribution, then it's like a log concave kind of distribution, and you can Vempella has some papers on how do you
Yeah,
sample from that. But it's not
right.
like a continuous object. It's like discrete paths. So
Yes,
uh,
yes.
yeah, so that's something I did look at, but that was the final conclusion that yeah, this is like a tricky term to deal with.
Hmm.
Yeah, so that's why we were kind of motivated to ask like, okay, what's going on here, like how can we, is there any computationally efficient algorithm which is also like kind of simple to interpret in some sense. uh, Implicitly we don't have to like go and look at exponential number of paths, so that was kind of the motivation, and obviously also to hit the same regret guarantees. So the question, the key question is very, like in terms of the algorithm itself, where can we hope to improve? In the sense that why is it the case that in the previous algorithm that I showed, they had to go for an exponential kind of algorithm, exponential weighted algorithm, because of the estimator that they're constructing. So if you look at this estimator that they constructed, it kind of goes well with this kind of algorithm, because once you start doing the calculations and all, the variance terms can be bounded in some sense. And also that's why they have to do this mixing. But they do that, like when that algorithm was designed, the common goal was that, oh, come up with a loss estimator y tilde such that in expectation it is equal to x by t. Like it's an unbiased estimator. And that has been a common approach for designing loss estimators. But the question is this like necessary? And the answer is no. And it's very simple to see. Like actually what you require is like the difference between like two vectors, x and x prime, and its inner product with y tilde should be equal to x minus x tilde inner product y t. And why that is the case? It's because what we are concerned is to minimize regret. And in regret, like it's a gap that matters, not the actual values. So when you okay, like on a high level, when you take the expectation, like when you take expectation of loss estimator, it becomes like actual loss, and then you can relate it to the actual regret and you'll be done. But actually the regret expression contains like a difference of two terms. So when you take like expectation of differences and when it is equal to the actual difference, then things will follow through. So this is like roughly the reason why like just doing this suffices instead of like having to do this. So this is what we'll be doing. We'll be constructing a different estimator such that this thing holds. Yeah, so let me get started with the estimator. So for the next few set of slides, let me assume for the simplicity that the number of edges on any path from source to sink, it is k. So I'm just going to assume that for time being, it will be pretty clear why I assume that, and then like it's also very easy to get rid of this assumption. Yeah, but this is like the assumption. So the number of edges from, or the length essentially from source to sink is k. This length is not the cost, like this is just the length, the number of edges. So okay. Like roughly at the start, Siddharth sir was kind of asking like whether I was playing a flow or a integral path. So during the algorithm, what we'll be doing is like first we'll compute a flow, and using that flow we'll like generate a path, integral path, and it will be done in a Markovian fashion. Essentially, what I mean by that is like when you say you're like choosing edges one by one, and in that process you reach some node v, then the probability with which you'll choose this next edge e doesn't depend on how you reach this node v. You can reach it in multiple ways, but the moment you reached v, you kind of forget, okay, how did you reach this node v, and just choose the next edge e in an independent fashion. Typically, like if you have computed a flow, then you choose it proportionally to the flow. So that's going to be the sampling process. And yeah, so this is like the Markovian way of sampling an integral path. And then this is going to be very crucial, like this particular way of sampling. So
it is like taking a random walk of sorts, right? Like
yeah, it's taking a random walk of sorts, yeah. And the weights of choosing an edge is proportional to the flow that's going.
Yeah. Okay. So it's different from the standard flow decomposition where you take a flow, write it as a convex combination of paths, and pick a path. Okay.
Yeah, and then they choose one of those paths or something like that. But yeah, that's not what I'm doing. I'm like kind of doing a walk. Yeah, you're right.
Okay.
And since it's a directed acyclic graph, you keep on doing this, you will reach sync ultimately.
Yes. Okay.
Yeah. Okay. So okay. So this is how I define the loss estimators for my DAGs, and this is in spirit very similar to what you do in the standard multi-arm bandits. Like in standard multi-arm bandits, it's like you have like loss and the indicator that whether you chose that arm divided by the probability that you actually chose that arm. So that is the standard multi-arm bandit loss importance weighting loss estimator. So in spirit here also we are doing something similar. So for an edge E, we'll be choosing like 1 plus LT times indicator that the edge E was chosen in my path divided by the probability that the edge E was chosen in the path. And for the node V, we are assigning a loss value which is 1 minus LT times indicator that the node V was chosen in the path divided by the probability that the node V was chosen in the path. And for the source and sync node, I'm just assigning 0. Yeah. And here LT is like the loss that you incur. The only reason I add like +1 here is that I want to keep the loss estimator non-negative, so that like some calculations work out in the when I do the analysis and all. So I required like positive or non-negative loss estimators for that. But this is what the loss estimator essentially looks like for the DAGs.
So this is like an importance sampling kind of a scheme.
Yeah,
But
yeah, yeah.
but the interesting part is like you have a loss for the vertices also. Can you explain why that is because your
Yeah, yeah,
adversary does not give you any loss on the vertices.
yeah, yeah. So that will be clear in the next slide. But essentially, if you look at this, like if once you start taking the expectations, you will. This is not an unbiased estimator of YTE. It will be pretty clear, but it is not an unbiased estimator of YTE. There will be some extra terms that are there. So the role of this guy is like there's a negative here. So the role of this guy is that even this guy, when you take expectation, will be generating some terms, and its role is to kind of cancel out some terms which are like kind of not required for us that are popping up here. So it is playing a canceling effect. So it will cancel out some terms which are not required, and it will only leave the terms which correspond to the weights of the edges of that path that you're concerned about from source to sink. Yeah. So yeah, so this is like the reason why like I'm introducing this extra representation. Like I'm also assigning a loss estimator for vertices, although it's not required because in reality there's no losses assigned to the vertices. But that's the motivation. So I'll be explaining that in the next few slides, like exactly how the calculations are shaping up. Any more questions? Otherwise, I can just move forward. Okay. Yeah. So under this Markovian sampling that I was just saying, I'll try to show this. Okay. So I'll be doing some calculations, simple calculations, based some conditional expectations kind of stuff. So first, consider this event that a path is passing through node V. So it contains the node V. So I want to do a simple analysis on how the total loss decomposes. Like if the total loss of the path from source to sink is LT, and how does it decompose? So obviously, like you can see, like you can decompose the path into two parts. Like one is from source to V, and then from V to sink. And so when you take the expectation, conditioning on the event that node V was chosen, then it just decomposes into the expectation of all subpaths from this source to node V, and then expectation of all subpaths from this node V to sink. So that's how it decomposes. So it just like splits into two parts. And similarly, now if you condition on the event that your path is now going through this edge E, then you can decompose it into three parts. This path from source to V minus, then this edge, and then this path from V plus to VT, which is a sink. And then again, you can split into three parts. This conditional expectation, which is the expectation from this part, then this edge value, which is YTE, and then this expectation from this part, which is this particular term. Now, a crucial thing to observe is that the expected value of a subpath from source to V minus doesn't depend on the fact that you chose edge E from here. That's because of the sampling that we are doing. Because once I reach V minus, the next step of sampling becomes independent of what I did here. And same goes for here. Like the expected length of the cost of the path from this node to the sink node, this does not depend on how I reached V plus. It just depends on the fact that I reached V plus, and then from there I just moved on. So essentially, this conditioning on the event that the edge E was chosen can be simply replaced by conditioning on the event that XV minus was chosen here, and conditioning on the event that XV plus was chosen. Like the V plus was chosen. So this is where I am kind of invoking that Markovian sampling thing. So now you can see that when you were dealing with vertices, you had this terms and this terms. And when you're dealing with the edge terms, you have this additional YTE term. So I somehow need to get rid of these terms. And that is why I introduced that extra estimator for the node V. And there's a minus sign there. Like if you recall, like there's a minus sign here. So they are now going to cancel out these terms, and you'll be left with these terms plus some additional bias that is coming from these plus ones. But yeah, like that is going to be the story. So I'll just finish the calculations pretty quickly. Like very straightforward from here. So like consider the path like V0, E1, V1 up to EK, VK. So there are like K edges in the path, where V0 is the source node and VK is the sink node. And when you start calculating the expectation of this term, it just splits into these two summations, like summing up from I equal to 0 for the vertices and summing up from I equal to 1 to K for the edges. And I'm just plugging in the definition of my estimators. And just take a small note that I equal to 0 and K have vanished, because for those estimators, I had kept a value of 0. And this is nothing but like conditioning on the event that Vi was chosen. What is the expectation of 1 minus LT? And same goes for this, like conditioning on the fact that like EI was chosen. What is the value of 1 plus LT? So I'll just finish the calculations for this. So you have this, and from the previous slides, I have this particular calculation happening. Like you open this up, and yeah, so you have this thing going on. Like essentially, like we did all those calculations there. So the plus ones kind of came out. So they are like 2K minus 1. And then you have this minus terms, plus terms, and you have the minus terms and plus terms. And they kind of start canceling out each other. And you're like golden. Like just like a small notation thing, which I should have said at the start. Like if you have like LT V0 minus, it's like what is the path length of the path from source to source, which is like 0. And same goes for like if you equate like k here, like what is the length of the path from sink to sink, that is also 0. So those extra two terms, they vanish, but rest of the terms, they cancel each other telescopically, and you'll be just left with summation of yt ei's. And so it's just the inner product of x comma yt, and then you'll have this term, which is like the length of the path in some sense. Like it's like 2k minus 1, and k was the length of the path. And so if the length of the path is same, then you can this extra term, they just cancel out each other because they are same for every path, irrespective of how you chose them. And so you'll have this particular equality to be true. Like it's like x minus x prime y tilde is equal to x minus x prime yt. So roughly speaking, these extra terms get cancelled by the terms that correspond to the vertex node, and you're like golden. Yeah. So any questions? I might have rushed a bit here, but yeah, happy to take. Yeah.
And so in summary, what you're doing is you're defining this new estimator y tildes, and you're defining them for both edges and vertices.
Yeah.
And they are far from unbiased estimators. Like they have an importance probability scaling going on, but they're not unbiased estimators. But the nice property that they do satisfy through is that if I look at the expected differences of the cost, not then I do get like the right term. So it's unbiased, but that bias is just dependent only on the length of the path and nothing else. So it cancels out.
Yeah, it cancels out. And and I'll show in the later slides very quickly, like if the path length is not same, still I can like somehow manage to do that same thing.
Yeah, you probably just adjust it by the length of the path.
Yeah. I do that exactly. Like I kind of append some extra bits to my representation to kind of balance this out. Yeah, that's what I do exactly.
And so now the point is that these estimators are conditional expectations.
Yeah.
So you'll have to show that they can be estimated. Like there's an efficient algorithm for.
So the algorithm is just like your FTRL. So what you do, like you solve this FTRL equation. So like you maintain, like you solve this particular optimization equation, and you choose your f of x to be a strongly convex regularizer, like Sally's half entropy or even negative entropy is also fine. And then you compute the flow essentially. And then using the flow, you generate the integral path. And that would be your algorithm. So all your computational efficiency is here. The fact that you're like doing an optimization over convex, like flow point up, you can like run those in, like essentially, like once you do the calculations, even you don't have to solve this exactly, you can come to a approximate, like you can come very close to the actual solution, and you will be fine. So we have like efficient solvers for doing that.
Yeah, it's a convex optimization.
Yeah, it's just a standard convex optimization. Yeah.
So basically, Arnab, to understand, the main trick is like to reduce this problem to this optimization of the flow polytope, and then coming up with efficient algorithms to sample from that flow like a path, and accordingly set the loss that will give you an unbiased.
Yeah. So that's the key step. Like come up with a loss estimator that satisfies this property.
Yeah.
And reduce the problem to this particular like problem on flow, and then sample efficiently.
And the sample efficiently because it's just a random walk.
Yeah, just a random walk.
Yeah,
in a Markovian fashion. Yeah. So this is the algorithm, and then this is like called the Sally's half entropy regularizer. I like this regularizer because like it does not, it has some good properties, which I'll tell at the end. But one immediate property is that it does not give you these extra log factors in general. Like if you're interested in expected bounds or something, I'll also say like how to get high probability. But this thing will give you stuff in expectation. But and still, this is not like the end of the show. There's some parts left. But even like this is like a, okay, like to the best of my knowledge, even in expectation sense, if I was looking at a family of directed acyclic graphs where the length of the paths were at most like k, then this is like the first algorithm that gets rid of this extra log factor that you would have got using like uh, like exponential weights for the DAGs. So this is similar to what happens even in the standard multi-arm bandits. Like exp3 gives you this extra log factor, whereas Alice half entropy won't. But yeah, like, but this bound in general, like, gives you like square root k et kind of regret bound, and the current version holds only an expectation. The way you get like a high probability guarantee, it's a very standard technique in Bandit. It's called implicit exploration. What you do is like you slightly bias the estimator, like you add some gamma e gamma v to the denominator, and you can get high probability regret guarantees. And this part is pretty standard, it's nothing new. uh, and instead of using y tilde, you use this y hat, and you'll get high probability guarantee. So you'll get this square root k et log e by delta with probability at least 1 minus delta. And uh, the funny thing is that even in multi-arm bandits, it is not known that if you want a high probability regret guarantee, whether you can get rid of this log k term that comes up like in multi-arm bandits. So in multi-arm bandits, you have like square root kt log k by delta when you deal with high probability guarantees. Whereas if you want expectation, you just have square root kt. So that is also like a interesting open question that's out there. But yeah, like if we don't care about log factors, which I don't care in this talk, the bound that you should take away for now at least is square root k e t. So this is the case, and as Siddharth sir was kind of pointing out, if you don't have like equal paths, you can kind of balance it out using the like by looking at the length of the paths. So essentially what I do is I kind of augment the vector by appending it some bits. And the way I append, so if I'm looking at some path x, then the way I append bit to it is that so for to begin with, I'll be maintaining some values, which is like the length of the longest path from source to that particular vertex v. So I'll call it as kv. So obviously the k source is 0, and kvt is like the length of the longest path. And what I do is uh, I'll augment the ith bit as 1 to my vector if there's an edge in the path such that I lies between ku and kv. Let me explain what is the intuition here. Like when is there an imbalance? Like uh, there'll be an imbalance if you take the longest path from source to u and add +1, and that is way smaller than the longest path from source to v. So this is like kv, and this is ku +1. So if kv is like much larger than ku, that's where the imbalance comes up, and I need to somehow fill in this gap. And I do this by like whenever I choose say such a path in such sense, then I kind of what I try to do, like there's an imbalance of kv minus ku minus 1 kind of, there's a gap imbalance of that much quantity. So the bits that I'm kind of appending, they fill this gap, because the number of bits that I append, at least with respect to this edge, is like kv minus ku minus 1. So those are the number of i's that satisfy this inequality. So roughly speaking, I'm implicitly balancing out the paths by appending this new vertices, and they can be done in an efficient manner, because all I need to check is whether this particular inequality holds. And that is very easy because I can just maintain the length of the longest paths. This part is not that important. It's just like neat arithmetic tricks. That's it. Yeah. And roughly speaking, corresponding to this extra bits, I will be maintaining an extra loss of 2 roughly. so that I balance out the actual bias that I'm introducing. So this part is kind of loose. And so essentially what happens is that you have this, which is the original representation, and this is the appended bits. And so this was the bias that was introduced originally, and my appended bits will introduce this extra bias. So this length of the path kind of gets cancelled, and you just have a fixed bias, which is the length of the longest path. So by kind of balancing out things, I can again get back the same guarantees that I promised you earlier. So this part is not that non-trivial. It's like kind of simple arithmetic going on in some sense. Yeah. Any questions as such, other like regarding this? I just went through it quickly.
So for this particular regularizer, is it? I mean, the flow polytope has some very nice structure. Like there are like tailor-made algorithms for it. So I'm just wondering if this, it's almost like a linear objective, which is like a like a min cost max flow, or like a unit like min cost flow. But I'm wondering if even with a regularizer, there is like, instead of using like a generic convex optimization idea, there's a tailored but very fast algorithm for it. Because that's probably your computational bottleneck, right? Like in this.
In this, that's the computational bottleneck.
Yeah. So I'm wondering if there is a like nice, but it's regularizer sort of also decomposes. It's like square root. It's like, then what? So you're putting some weights on the vertices of the path and some
appended bits.
Bits on the edges, and then So I'm wondering if you can just, in fact, reduce it, given this nice form of the regularizer, reduce it to like a standard flow problem itself, like a min cost flow.
Like, so you mean like coming up with a combinatorial algorithm for it?
Or in fact, reducing it like to a like with these adjusted weights to a standard quote flow problem, like for which like strongly polynomial or very fast algorithms are known.
I do agree. Like this algorithm does not have any strongly polynomial kind of thing. It's just like it is as good as your interior point method kind of algorithms.
No, but still very fast. But I'm just curious.
But I think I did not completely work out the calculations, but I saw some paper where like they were talking more in the MDP setting, but I think that idea can be used here as well, which is like at each node you run an EXP3 algorithm locally, like the multi-arm-banded EXP3 algorithm over the outgoing edges, and you set the losses of that of those edges in a particular manner, and that might be way more faster, like computationally speaking. But I did not explore that particular approach compared to this. So this was the case, but still this is not like the end of the story, because if you recall right at the start, the bound scaled as square root et log cardinality of x. So the thing is that this particular bound can be looser than square root et log cardinality of x, where x is the set of paths. And to show why, like consider this graph where you have like a straight path, and then you have a like a direct edge from this every node to the sink. So the length of the longest path is roughly order e, because they're like only like roughly or number of edges is like linear in number of vertices. So like that's why I just called it order e. And our algorithm will give you like e times square root t regret, whereas a minimax optimal algorithm like exp3 will give you square root et regret. So there is still a gap between this and this. So I'll quickly just say like how do I fix that thing. So as a motivation, just consider the same toy example. You could have kind of converted this into another DAG, which kind of does a one-to-one mapping between the paths here and the paths here from source to sink. So for example, this entire long path, you could have just like brought it out and called it like this particular thing. Oops, sorry. And then like other parts, like there are only like, for example, in this simple example, there are only like order key paths. So you can just like separate it out in some sense. And you can like kind of like you can construct an equivalent problem instance such that the paths are one-to-one mapped and the costs of the paths are also like equal. And so instead of running your algorithm on this, we can run our algorithm on this. And in this graph, k is equal to 2. So I can just recover square root et kind of guarantee. So the goal is this essentially, that we start with our graph G and we kind of construct an equivalent graph G. I forgot what that symbol is, hammer or something, dagger. Sorry, yeah, G dagger. Yeah, and when I say equivalent, what I mean is that the path here from source to sink should have a one-to-one mapping to the paths here from source to sink. And given any weight assignment here, I can construct a weight assignment here such that the cost of any path here is equal to the cost of the equivalent path or the path that it maps to here. So that was the goal, and what our aim was to reduce the length of the shortest path. So you start like if you have a maximum path length which can be arbitrarily large k, then what we do some kind of conversions and ensure that the length of the longest path is just log cardinality, and the number of edges kind of remains the same. Like this O tilde just hides some logarithmic factors in E, not log calyx. Like log calyx is pretty huge, but in terms of log E, we are fine. So we O tilde just hides some extra log E factors. So we are not like blowing up the graph too much, but we are kind of compressing the path length and keeping the problem equivalent. And in that case, if we run our algorithm on this graph instead of this graph, then we'll get a regret which scales as square root et log cardinality, where the k, earlier we had ket, now that k gets replaced by log cardinality. So this is what we also do in our paper. I did not keep a solid slide for that. Like I kept this slide, but I'll just give a high level intuition on what we ended up doing there. But before I go, any like questions around this?
So, now, like, I mean, key, like, can you compare the quantities k and log cardinality and like tell us, I mean, in what instances which is more, and I mean, why is there benefit to going to log cardinality? Because I meant, yeah.
So the log cardinality is always less than k, or like roughly is roughly less than equal to order k in some sense. You can do this calculation because if you don't care about log factors, then like, so you have say d bits or e bits in your path, and you need to choose k of them. So the maximum number of paths that you can have is roughly e to the power k. So log cardinality is roughly is at most k, but in some cases like this one, the length of the longest path is e, but the number of paths from source to sink is also e. So in that case, we can save on a factor of square root e. So there can be a huge saving that one can do by switching from our original algorithm, which is a square root ket, to this particular algorithm where we like convert it into another DAG and we reduce the path length.
Can you give some intuition about this reduction in the previous simpler graph that you showed? Maybe I missed that in the previous graph.
Yeah. So in this, okay, this is I just like, okay, this is all I did here was like, okay, the number of so okay, let V be the number of vertices here essentially. So the number of paths from source to sink is V or V plus 1. Like I'm not doing the calculation correctly. So that's the number of paths from source to sink in this example, which is also like order E because V and E are of same order. So the number of paths from source to sink is order E. So what I did is that I can just treat each of them as a single multi-arm, like arm separately, like just treat each of them as order E different arms, and that you can just rewrite as a DAG in this particular fashion. So this is like choosing your arm 1 or path 1. This is like choosing a path 2 and so on. So you have like order E paths, and your length of the maximum path, like length of any path is like 2. So I can just have like square root ET, and the weight, like just like assign the weight of the path here to one of the edges. So if this, yeah, so that was the intuition. For this, it was pretty clear, like how do I do? But for arbitrary DAGs, it's not so trivial to see how do I make this conversion happen. So that was also one contribution in our paper, which might I like, yeah. Yeah, maybe I'll just give a very high level view. Yeah, it's a slightly complicated procedure, so I did not like dive deep into this because my focus was to keep it mainly around the learning theory talk rather than a graph theory talk. But roughly speaking, what we are doing is like we are kind of doing some decomposition based on the centroid decomposition. So what we do is like we begin with the original directed acyclic graph and we kind of construct a spanning tree out of it to begin with. And the way I kind of choose this spanning tree is that for each vertex, I see, okay, which incoming edge brings me the maximum number of paths to me. So that is the way I'm like choosing these edges of the graph. Now, the advantage of doing such a thing is that if you consider any path from source to sink here, the number of edges which are not kind of considered in this spanning tree will be like log cardinality. So you can do the math easily, and that's how we'll go. Like that is a very crucial fact for us in order to decompose the graph and kind of compress some parts of the graph and get a path length which is like log cardinality. So essentially what we are doing is that there are some portions of the graph where a lot of paths are going through one particular edge or something. So you can kind of compress things in some sense without having to extend the graph length. So what I do is like whenever I construct this spanning tree, I choose the centroid. The centroid is a point like node which kind of splits the graph roughly into two parts, equal parts, and I keep on doing this. And then once I reach like to the lowermost decomposition, I kind of start reconstructing the paths upwards. So essentially, for example, for each node, I keep like 3 copies, say 1, 2, 3. And if there is an incoming edge, so I start from the first node and bring it to the second node. Oops, sorry. And if there is an outgoing edge, then I start from the middle node. Like these black nodes are centroid. So what happens is that in a tree, if there's a centroid decompositions, all the children, they connect. Okay, so for example, okay, what is the key idea? Say this is a centroid, and some guy needs to go from here to here. Okay, now if you look at this path, it's pretty huge. Okay, so if I want to reduce the length of this path, ideally what I should do is that I do this decomposition, and I should ideally create a direct edge from A to D and then from D to F. So that would drastically reduce the path. So if you do this kind of centroid based decomposition, your centroid, so if you want to go from one part of the tree to the other part of the tree, instead of directly going to that other part, it's like you go first to the centroid and say, oh yeah, hey, I want to go to that part, so I'm first reaching out to you, and then you first reach out to this guy, and then from here you go to this guy. So that's what happens here. So from A, we end up going to D because there is a path from A to D, and from D we end up going to say H. So in some sense we are kind of compressing the path length, and this can be done in an efficient manner first, and this can be done further in a manner that does not explode the number of edges that we have in the graph. I'm like kind of skipping how why that's true. But yeah, so this is like the motivation that we have, and we do this conversion and we end up with this graph at the end. And then this graph has these all properties, and you can like then run our algorithm and get the guarantees. So if you're interested, I would suggest strongly that you go and read this particular part. It's very interesting, but for time and all, I'd skip the details. But if you have any questions, let me know. I can answer.
It's also sort of a counting thing, right? In the sense that you have cardinality of calyx paths. So you need like log that many bits to represent it.
Yeah, that's true.
So I mean, in some sense, you're saying I can construct a graph where the path lengths, like the 0, 1 kind of. I mean, just imagine like a layered graph where you either choose the top edge, the bottom edge, the top edge, or the bottom edge. And so the binary representation somehow gives you like the so all path lengths are, I mean, just imagine like a chain of vertices where between every consecutive vertices you either have a top edge or a bottom edge. So it's like a binary representation of every possible path in the original graph. And so somehow you're saying that I can construct a graph where not only is the counting going to work out, but there's a corresponding.
All those meaningful properties are also going to be written.
Yeah, I see.
Yeah. So this is a fairly non-trivial conversion. Yeah. I kind of skipped because I was more in like I like the learning part more than the graph theoretic part. So but yeah, like the details are there in our paper in a straightforward manner. So yeah, if anyone is interested in the graph theoretic part of our paper, then this is the thing to look at. But this also raises a nice question in the sense that essentially what we are doing is like we are making the vector sparse in some sense. By saying that the length of any path is log calyx, it's saying that the number of ones is at most log calyx. So it's like what we ended up doing like mathematically is like we took the original set of vectors and made it sparse, and on that I ran my algorithm, and that's the thing. So does this approach generalize to other sets as well? Like essentially you have to sparsify things in some sense while keeping things equivalent between the original set and the new set. So this is the thing, and I'll quickly wrap up the talk. Like our techniques can also be applied to other combinatorial sets, mainly because you can take these combinatorial sets and convert it into a directed acyclic graph. So if you have hypercube, you just have like you keep two options and you just go, and then you have like M sets where like the number of ones in the vector is exactly M, and even this also gets captured. And then you have like extensive form games, even that also gets captured by DAGs. And then there are some resource allocation games like colonel blotto game and all, like where you have like n resources and you have to distribute across k places, and then you incur some losses and all. And for all of them, the previous best known guarantees were like relatively high in terms of high probability sense, and we kind of brought it down. So for some of them, it's like actually quite optimal, and for some of them, it has improved the regret bounds, but there's still scope for improvement. Uh, and this takes me to the open questions. like, can one extend our approach to arbitrary combinatorial sets? Like we had like two things going on. We had this unbiased, like difference-wise estimator thing going on. And yeah, and also this pacifying kind of thing. So can you take it, like, can you extend this approach to arbitrary combinatorial sets? Like the thing is that in the linear banded framework, even in the combinatorial set setting, there are only like two kind of algorithms that are known. One is like the exponential weights that I presented at the start, and the second one is like an FTRL algorithm, but the regularizer is very, very specific. Like it's like a self-concurrent barrier. So this FTRL only works with that particular barrier, and it has some flaws in it, and it definitely does not give the optimal guarantees as well. So whereas this approach that we presented, it is like a more generic framework. Like I'm giving you an FTRL framework where I did not even specify at the start what that regularizer is, because any regularizer works. Like I can use log barrier, I can use Saris half entropy, I can use negative entropy, I can use any other regularizer I come up in future. So it's a very flexible framework. And also, like, if you manage to extend our approach to some arbitrary sets, then what happens is that there, like for any combinatorial games, like in the game community, they're pretty much interested in like last iterate convergence to Nash equilibrium and all in zero-sum settings. So there'll be some interesting results that will automatically come out if one manages to extend our approach. And then the second question is like best of both worlds. So by that, what I mean is like in the standard multi-arm bandits, you have the square root kt regret bound in the adversarial setting, and in the stochastic side, you have like log t by gap kind of regret guarantee. And it was shown like 4 or 5 years ago that if you use the Salis half entropy, then the same algorithm gets like optimal regret guarantees in both adversarial settings and stochastic setting. So that's why I said that Salis is one of my favorite regularizers, because it has some nice properties. So the analogous question is, can one do something similar for DAGs? Recently, I had a submission in Eurips where I was doing something similar for DAGs and MDPs, but the thing is that for DAGs specifically, the only thing that we cared was that, oh, in the adversarial we get square root t regret, and in the stochastic we get some log t regret. But we didn't actually care about whether the terms associated with, say, square root t, they were optimal, and similarly for log t. So in that sense, the problem is wide open. Like, can you give like optimal guarantees for both sides of the world using one single algorithm? And then there are these resource allocation kind of problems, and for that, can one design like efficient algorithms with minimax optimal regret? And the last question is way more fundamental. Like, if I give you an arbitrary set calyx, how does the regret actually scale with respect to the geometry of this set? So this is like a very wide open question. But yeah, so these are some of the questions. Yeah, and thank you. And if you have any more questions, let me know.
So, and like for this combinatorial part, like let's say for 4 and 1, like are matroids studied in the same? So
yeah,
the model
look,
is used.
Yeah, I have. After I kind of submitted my paper, I tried to look at matroids also. I don't think it has been studied in great detail, in my opinion. Yeah, they are kind of left to be studied. Yeah, like I don't think they have been studied. I did try to look into the literature to see if there's something that can be done there, but they haven't been looked at. Yeah.
But I mean, yeah, the interesting point would be that, like, unlike say paths and DAGs, like maximum independent set would, all of them would already have the same cardinality. Like, so these sorts of properties you do just inherit. Like all, like the largest cardinality-wise independent sets will have the same cardinality. So I mean, okay, just a particular instantiation would be, you, instead of picking paths, you pick a tree in a graph, like a spanning tree, and then get to see its weight. So yeah,
I see.
So graphic matrix, like which is like you pick a spanning tree and again the adversary sets the weight of the loss on the edges.
Yeah.
Observe that. Okay. But you're seeing like not too much literature is around this.
Yeah. Not too much literature is there on this. Yeah.
I think in the stochastic setting, this has been studied, but not in the adversarial. Maybe not in the adversarial.
Okay. Yeah, I mainly meant in the adversarial. Yeah.
So stochastic, like the edge weights
The edge weights are
like distributional. Okay.
Yes.
Okay. Nice.
And the reason I also asked this last question was, if you look at this particular problem, which is called multitask multi-arm bandit, which is just like I'm taking the standard multi-arm bandit and I'm doing a Cartesian product of those sets. So Cartesian product of probability simplices. So the kind of bound I get is like square root dit summation I equal to 1 to m. And this can be way smaller than square root dt log cardinality. So it kind of says that, okay, square root dt log cardinality is not the final answer. Like, because like, okay, I'm not going that far, but essentially like when they run this exp3 and all, and they give you this guarantee, which is square root dt log cardinality, that is like mini-max optimal, which means that, okay, there is some problem instance for which this figure is optimal, but that doesn't imply that for every possible set, it is optimal. So that's why I asked this fourth question also, like, okay, for any arbitrary set, what is the optimal regret actually scaling as? And this is, I'm not even asking computationally efficient approach or anything. I'm just asking any algorithm. And there's no like work done on this, like in any fashion.
Interesting.
Yeah, but that's a very challenging question. I don't know like how to even approach this particular question. Yeah.
Thanks, Arnab.
Yeah.
Thank you.
Yeah, thanks a lot for inviting. Yeah.
Is this preprint up there somewhere?
Yeah, it's up there. Yeah, I can like send it in the link to Nijar. Yeah.
Yeah. We'll put it up on the website.
Yeah, I'll just send you in a moment. Yeah.
I'll stop the recording. Rest of
Yeah.
the questions we can have in an informal setting.
Yeah.